Just want to make a quick video to show how we can take standard binary search and extend it to be able to answer all sorts of binary search questions while maintaining logarithmic time. Instead of just asking, does this element exist within the array, it would be nice to also be able to answer, well, what is the index of the first instance of this element in the array, or the last index? Or what is the largest element that is smaller than our target item, or the smallest element that is larger than our target item? Or maybe we want to ask, if we were to insert this item, what index would it end up at? What index would it end up at if we inserted it to the left of any existing items? And what index would it end at if we were to insert it to the right of any items with the same value? I'm hoping to show you a single model here, a single method where we make a slight modification to the standard binary search, which will enable us to answer all of these questions. And I hope to do it in a way that doesn't require rote memorizations to be able to use all the different variations, but rather to provide you with some intuition so that you can pull out the correct solution during your technical interview or during your career. So let's get started. On the left here, if I were to take this and say, well, let's say if items mid equals target, then return mid, and here we were to return none. This should be the standard binary search algorithm, right? So we have a left pointer at index 0, and I do this inclusively, so our right pointer is at index 6. And we're going to find the middle of those two pointers, which is index 3. That has a value of 3, therefore we should return index 3. Run this here, and we see we get an output of index 3. So that's standard binary search, but the index that it returned isn't any specific 3, right? It's not the first 3 in the list or the last 3. In this case, it happens to be the middle 3. That's not very interesting to us. It's not very sexy. So let's go ahead and delete that. And we're also not going to return none here. Instead, we're going to modify this so ultimately we'll be returning either the left or the right pointer, depending on the question. Okay, so the rest of this algorithm is the same. And let's say that we start out here and we say, well, if items are less than or equal to our target. So if the middle item that we're pointing at has a value less than or equal to our target, we're going to move the left pointer 1 to the right of the middle pointer. This actually encapsulates in it an invariant. And what is that invariant? It says that when this algorithm is done running, every element that is less than or equal to our target value, less than or equal to, is going to end up to the left of our left pointer. Similarly, implicit in the else statement here, every value greater than our target is going to end up to the right of our right pointer. What does that give us here? Well, 1, our right pointer, if our target value exists, our right pointer should be pointing at the last instance of it, right? So that would be index 4 for a target of 3. And sure enough, our right pointer is pointing at the last instance of the target. Our left pointer, if there is a value greater than our target, our left pointer is pointing at the index of that value. Interestingly, the index of that value, if we wanted to insert another instance of our target of 3, that left pointer is pointing at the index that it would end up at. This is identical to the bisect function within the bisect library of Python. Let's take a look at that. So if we import bisect, and then we say bisect.bisect or bisect.bisect right, they are the same. And we pass in our items, and we pass in our target, we are going to get an index of 5. Well, our left pointer, after running this algorithm, is also pointing at our index 5. So there is a LeetCode question that asks, find the next element the smallest element larger than the target, this algorithm just solved it. Our left pointer is pointing at that next element if it exists. Similarly, if we wanted to find the last instance of our target, the right pointer is pointing at it. If we wanted to find the index, if we were to insert a new element and it should go to the right of any existing elements of the same value, the left pointer is pointing at it. Okay, so we've solved 3 problems here. We've also mimicked an implementation that exists in a Python library, the bisect right. What else can we do? Well, let's say we were to change the invariant. Originally, our invariant said that anything less than or equal to our target value would be to the left of our left pointer. What happens if we change the invariant such that everything less than our target value is to the left of our left pointer? Well, again, that's going to implicitly change it so that everything greater than or equal to our target value is to the right of the right pointer. Okay, so if our target is 3 and everything less than our target is to the left of our left pointer, and everything greater than or equal to our target is to the right of our right pointer, now what do we have? Well, 1, we see that our left pointer, if our target exists within this list, our left pointer is pointing at it. Index 2 is the first instance of 3. So now we've seen we can find both the first and the last instance of a target value using binary search. Similarly, our right pointer, if there is a value smaller than our target, the largest of those values is what our right pointer will be pointing at. So in this case, it should be index 1, pointing at a value of 2, and there it is, index 1. What about the question of bisect? Well, if we wanted to insert a 3 and we wanted to insert it to the left of any existing 3s in the sorted array, what index would it go into? Well, it would go into the index of any current 3 if that existed, right? So our left pointer, which is pointing at the first instance of the 3, is also pointing at the index that a new 3 would go into if we wanted to insert it to the left. That is what the bisect left function in Python does. Bisect.bisectLeft tells us the index that this item, the item 3, would go into if we were to insert it sorted into this sorted array. Now, I have been doing a little bit of hand waving here, which is that I haven't addressed the case where the target value doesn't actually exist in the list. What's the problem with that? Well, let's say we'll keep this here. We'll return the left value. Maybe I think this is less than or equal to, let's say we're searching for a target of 1. And actually, here's what we're going to do. We'll keep this less than. So we're saying that everything less than our target of 1 ends up to the left of the left pointer. Everything greater than or equal to our target of 1 ends up to the right of our right pointer. So our left pointer is pointing at the first instance, and in this case, the only instance of the value of 1, right? At index 0. The target of 1 does in fact exist at index 0. Now, what if we want to search the target of 0? 0 doesn't exist in this list at all. So what should our function return? Well, in this case, our function also returns 0. Now, clearly that isn't correct. What is it correct for? If we were to insert a 0 into this list, if we were to bisect the list and insert 0, it would belong at index 0. However, if we were searching for the first instance of 0, this answer is not correct. So this highlights one thing, which is that after we did this, let's say that this was the algorithm searching for the first instance of the target, what we might want to do here is, let's say that this is our index, right? We might also want to say that, well, if index is, greater than or equal to 0, and index is less than the length of our item, so we make sure that we're actually pointing at an index that exists in the list, and that items at index equals our target. And if this isn't the case, then we should return none, right? We didn't find it. Else we can return index. And these aren't returns here, right? Like in this case, we're probably trying to print, so we aren't inside of a function. And because this is inside Jupyter Notebook, we will just go ahead and print these values here. Okay, so now we see, okay, we're searching for target 0. It doesn't exist in the array, therefore we get value of none. If we were searching for a target of 1, we would know it was at index 0. If we wanted 3, it would give us the first element, which is at index 2. However, if we wanted to find the last instance, as we went over at the start of this video, and everything less than or equal to our value was to the left, everything greater than our value was to the right, and we returned the right pointer, then here we could see we could very quickly change this so that we were pointing to the index of the last instance of our value. And all the same, if we were to be searching for 7 here, we would see it didn't exist. Now, this is nice for the case where we're searching for an instance and we want to make sure that we actually found it. But without this, we do still have the bisect function, right? So if we had a target of 9 and we were to run this and we just wanted to print this, so get rid of this here, we'll see that target 9 should exist at index 7, right? Index 7 isn't actually in this array. However, if we wanted to insert 9 into the array, into the sorted array, it would end up at index 7. So depending on what your use case is for binary search, you can make this differentiation. You can very easily see, and I might go ahead and make a second video that shows this, how we could then make a library, which would extend the search function of an array where we could assume that we had a sorted array and we would be able to find all elements with all sorts of variations applied to this issue.